Okay, good morning, good afternoon, good evening. It's Dr. Kaz here, and I'm bringing you another installment for fluid electrolyte and pH balance chapter. So in my last video, I kind of went through the major electrolytes, where you find them, what they do, and how we regulate them. And I've talked about potassium, but I don't really feel like I covered it very well. So I'm going to start with potassium again and continue on. So let's talk about the potassium ion. All right. So here we are, we're dealing with potassium. And as you recall, in previous videos, I had mentioned, think of potassium when we're dealing with our cellular structure as a banana floating in the ocean. We know that bananas are high in potassium. So we're going to find the majority of potassium in our bodies are going to be located inside the cells. So you can see about 98% are going to be in the intracellular fluid, and then about only 2% will be in the extracellular fluid. Now, this gradient, this difference in potassium distribution, right, is going to be maintained by none other than the sodium-potassium ion pump. And so this ion, it's a positively charged ion, so therefore we call it a cation, is going to be responsible for creating that osmotic pressure, that pulling osmotic pressure of drawing water into the cells here. We know the value of potassium because it does play a role in the generation of action potentials and that distribution of potassium in and out of the cell. So we do need it for anything that is neuromuscular related, and it also plays a crucial role in controlling our heart function, the rhythm, the beat of our heart. So really, when we're dealing with potassium, since the majority of potassium is located inside the cells, the only portion that can be regulated is the potassium that we find outside the cells in the extracellular fluid. The normal range for potassium is 3.5 to 5 milliequivalents, right, per liter. That's what we're going to, when you get your blood drawn and they're checking in the blood plasma your potassium levels, that's what they're going to be looking for. So this electrolyte, if there are significant imbalances going on, this is the most lethal of the electrolyte imbalances, and it can cause heart issues and lung issues or respiratory arrest there. So when we're talking about our total body potassium, right, again, we're going to regulate potassium through the intake of potassium and its output. Primarily, the input for potassium comes from the diet. So roughly what we want to do is take in about 40 milliequivalents, primarily through fruits and vegetables. That's why it's important, right, folks, to have a well-balanced diet. In addition, you should be consuming, and I am guilty of this, of not eating enough fruits and vegetables. So the majority of the potassium that is lost or that is found in the output is going to be lost in the urine. And if that, of course, fluctuates depending on, right, what our potassium levels are going to be in our blood plasma. So we'll see greater amounts of potassium being lost in the urine if we have high blood plasma potassium, right? Also, if we see there's an increase in aldosterone secretion, or if our blood pH is elevated. We're going to talk about how we distribute potassium and how it fluctuates and regulated here just in a few moments. So we're going to have, when we're dealing with the potassium distribution in the intracellular fluid and the extracellular fluid, we're going to keep that at a specific ratio where the majority of potassium will be found inside of our cells, right? And the minority, very little, will be found in the interstitial fluid and in our blood plasma. And so what helps to regulate this is going to be our sodium-potassium ion pumps. And then we can't forget about our other transport proteins, the potassium leak channels. They also do play a role in that potassium distribution. So potassium is going to shift into the cells, all right, from the extracellular fluid. And we'll also see it shift from the cells, from the intracellular fluid to the extracellular fluid. So there's certain conditions that are going to cause this to occur. And so the three conditions that we're going to talk about is, one, if we see a change in our blood plasma concentration of potassium. Also, if our blood plasma hydrogen ion concentration changes, that will affect, all right, potassium shifts in and out of cells. And then finally, if there are specific hormones located in the blood, those too will influence, all right, that shift in potassium, either into the cells or from the cells into the extracellular fluid. So when we see an increase in our blood potassium levels, we call that hyperkalemia. So an increase in blood potassium levels is called hyperkalemia. And so what we'll see in that scenario is that the potassium is going to want to shift from the blood plasma into the intracellular fluid. So it goes from the ECF into the ICF. When we see a decrease in our blood potassium levels, we call that hypokalemia. And again, potassium is going to want to move from the cells into the blood plasma. And so we'll see a shift of potassium from the ICF into the ECF. So a couple things that are going to affect the potassium shifts. One is going to be the blood plasma concentration, right? That's the first one. Now, what about our blood plasma hydrogen ion concentration? Well, when we see an increase in our hydrogen ion concentration in our blood plasma, right, that's going to decrease the pH value of our blood plasma, then we're going to notice hydrogen ions are going to want to move into the cells. And as a result of that, because we want to maintain this electrochemical gradient that is being generated because hydrogen ions have that positive charge, we want to exchange those hydrogen ions as they move, all right, in this scenario, from the ECF into the ICF. We want to maintain that positive value. So we have to find another positively charged ion, and that's going to be our potassium. So if the hydrogen ion moves into the ICF, the ECF is losing that positive charge. We're going to want to replace it with the positive charge from the potassium. So the potassium is going to move out of the cell and it's going to move into the extracellular fluid. And the same thing will happen, all right, if we have decreased hydrogen ions in our blood plasma, right? So that whole scenario will change. I'll show you a picture in a moment here. And then the final thing that can cause, all right, potassium shifts are going to be certain hormones. Now, the hormone we're going to talk about here is insulin. As we know, insulin is going to regulate our blood glucose levels, all right, blood sugar levels. So what we'll see is, as we know, insulin is going to decrease blood glucose levels. It encourages cells to uptake glucose. So with insulin, we'll get a decrease in blood glucose levels, but at the same time, we'll notice that we also get a decrease in the potassium ion concentration in our blood. That is one of the effects that insulin has. And the reason why is that it stimulates the sodium potassium ion pumps. And so this is going to increase the movement of potassium into the cells. So it's going to leave the blood and enter into the cells. And this is important because this helps to prevent hyperkalemia. Remember what I said, okay? This ion, potassium ion, is one of the most lethal electrolytes that we have because it is going to affect your heart rhythm. So if you are hyperkalemic, you have these elevated potassium levels, this could cause a problem. And so your body wants to offset that by getting the potassium out of circulation and get it into the cells. And so that's one of the effects that insulin has. It is going to decrease your circulation of potassium in your blood and increases cellular uptake. This will usually happen after a meal because the insulin is being released. So just to show you, I'll show you a picture involving all those potassium shifts here in a moment. But again, we're looking at our potassium balance here, right? How do we take in potassium? Pretty much through the diet, through the food that you take, or even maybe some supplements that you are taking. And then, of course, the majority of potassium is lost through our urine, but we'll also lose it through feces and our sweat. So a major hormone, all right, that is affected by our potassium levels is going to be aldosterone. All right, that is the number one, in fact, all right, a stimulus to aldosterone secretion is going to be potassium levels. So what we'll see here is with aldosterone, once aldosterone is being secreted, right, it's going to cause our kidneys to secrete or excrete potassium into the urine. And by doing so, it will then decrease our blood plasma levels of potassium in circulation here. So this hormone does help to regulate our potassium blood plasma concentration. How does it do so? What we do is we just excrete it into the urine and it decreases that blood potassium concentration in circulation. So these are those three things I was telling you about that causes the potassium shift in and out of cells, right? So again, what we're trying to do is maintain normal blood potassium levels. So if potassium starts to increase in concentration in our blood plasma, then what we're going to do is we are going to move that potassium into the cells. And vice versa. If we become hypokalemic, if our blood plasma concentration levels for potassium decrease, then we're going to move potassium from the cells back into the blood. Another way that we can redistribute or shift potassium in and out of the cells is when we're dealing with our pH of our blood here. So if you notice, all right, the pH of the blood starts to decrease because our hydrogen ion concentration increases, then we're going to move those hydrogen ions from the blood into the cells. In doing so, we're removing a cation ion, a positively charged ion, and we want to maintain that electrochemical gradient in circulation. So how do we do that? Well, we're going to swap out a cation ion for another cation ion, and we get that cation ion from the cells. So as hydrogen ions move into our cells, potassium ions will exit out of the cells, and vice versa. If our hydrogen ion concentration, all right, starts to decrease in our blood, that means the pH will increase, then we are going to move hydrogen ions out of the cells into circulation to help to return that pH value to the normal level there. And in doing so, we're going to swap out one cation ion for another. So as the hydrogen ion is coming out of the ICF, then our potassium ions have to enter into the ICF. And then finally, all right, we talked about how certain hormones are going to affect the distribution of of potassium, right? And so the example was insulin. And what will happen is insulin is going to decrease your blood glucose levels, especially after a meal. And as a result of that, glucose is also going to move potassium from the blood plasma into the ICF, just to make sure that you don't have elevated levels of potassium in the blood, trying to prevent your blood from becoming hyperkalemic. All right, so let's move on here to the chloride ion. That is our next electrolyte that I want to discuss. And of course, most of the time when we discuss chloride, we are going to, normally when we discuss sodium, right, it's hard not to talk about chloride also, because together, right, they form salts, sodium chloride. And that example, going back to what I've said before, right, about the banana floating in the ocean, the banana represents the cell with the potassium and high concentrations on the inside, but floating in the ocean has to do with salt water, the seawater, which has high concentrations of sodium and also chloride. So now we're going to talk about chloride, right? We know that sodium and chloride are attracted to one another through those electrostatic interactions there, right? Opposites attract. And so what we're going to see is basically where sodium goes, chloride wants to follow. And so when we're dealing with the amount of chloride, all right, that is lost in our urine, it really relies heavily upon how much sodium is in our blood plasma. Right, we do notice, right, that we need chloride for several functions. All right, how else? I mean, for digestion, for example, it is one of the ingredients for one of the digestive secretions in your stomach, hydrochloric acid. So we need chloride for our stomach secretions. But if you've ever noticed, right, on a day that you have been exercising quite strenuously outside or inside, and you start to sweat a lot, all right, sweat is salty. That is because it contains both sodium and chloride. So we will get a majority of our chloride through our diet. Certain foods, I mean, there's folks that like to put salt on everything. So if you're putting salt on your food, you're definitely going to get a pretty decent amount of chloride in your diet, right? But you will lose that chloride through the processes of sweating, through stomach secretions like hydrochloric acid, and then of course we'll lose it through the urine there. So when we see increased levels of chloride in our blood, okay, we call that hyperchloremia. And then our decreased levels of chloride in our blood, that is called hypochloremia. All right, the next electrolyte is calcium. Calcium is very important to have in our body for several reasons. We need it for the proper function of the neuron. We also need it for muscle contractions, for the clotting process, and it's also a very important ingredient in our bones, all right, and teeth. So we will find quite a bit of it in both of those structures. Think of your bones as just a storage site for calcium. The majority of it is going to be stored there, about 99%. That's quite a bit. Right, then we'll find, right, calcium is going to be found, right, outside of our cells in the interstitial fluid, or it'll be found locked away in the sarcoplasmic reticulum of our muscle cells there. And so one of the things, all right, that's important about calcium, right, is that it helps to prevent phosphate, right, from hardening inside of our cells. Now, there's certain conditions, and I won't really get into it right now, which you can get accumulation of calcium inside of certain tissues. And a lot of that occurs because calcium interacts with phosphate. Phosphate's found on the inside of the cell, all right, in large concentrations. And so if we can separate calcium from phosphate, that's a good thing, because if calcium gets inside, right, and I've mentioned this in other videos of mine, that calcium, if it's invited to the party, it's going to start to harden things up. And we talked about that when we were talking about osteogenesis, right, how we talked about bone formation, that when calcium starts to move into our calcium matrix, it causes the calcium matrix to harden. So we don't want calcium finding its way into the cells, because if it does, it's going to hang out with phosphate and it's going to start to harden, and it can cause damage to the cell there. All right, so how do we get calcium? Right, primarily through, again, our diet, right? And then we'll lose it through primarily urine, but also feces and sweat. So increased blood calcium levels, we refer to that as hypercalcemia, and decreased blood calcium levels, we refer to that as hypocalcemia. So speaking of phosphate, right, that is calcium's partner in crime when we are making bone tissue, the hardened bone tissue, that hydroxyapatite. All right, the phosphate ion is going to be found in significantly high concentrations inside of our cells. Right? It is the most abundant anion inside of our cells. And so 85% of it is going to be found, all right, mixed up with calcium inside of our bone and teeth. We'll also see it in our DNA, all right, RNA, and also the phospholipids. You remember the phospholipids, those are the lipids that are going to form or be a major component to the plasma membrane of our cells. Now, phosphate is a wonderful intracellular buffer. Okay, it will help with regulation of the pH inside the cells, and it also is a buffer in our urine here. So most of the phosphate that is going to be found outside of our bone and teeth is going to be ionized when it is in outside the cells in the blood plasma. Right, then the remaining amount is going to be bound to the transporter carrier proteins there. All right, so what we'll see is when we regulate, all right, phosphate, simple to remember, it has the same regulatory mechanisms as calcium has. So pretty much what calcium does, phosphate will do the same. Magnesium, one of my favorite electrolytes. And the only reason why, not the only reason why, but one of the many reasons why calcium or magnesium is a wonderful electrolyte is because it is found to be involved in not just hundreds of enzymatic reactions. I want to give you a better number, anywhere from 700 to 800 enzymatic reactions in your body. That's a lot. That's why magnesium concentrations are so very important. Magnesium will prevent calcium from going into the bones solely, right? It helps with the proper absorption of calcium, right? But it's also important in the production of ATP. So we're actually making ATP. Magnesium is involved with that. So where do we find magnesium? Again, primarily in the bones or in our cells. So it is the second most abundant cation inside of our ICF. Right? It does help with the proper functioning of the sodium-potassium ion pump. We do need it for muscle relaxation. Like I said, we also need it for that ATP production. All right, so where do we get, all right, magnesium? From our diet, primarily from beans and peas, but green leafies. Our green leafy vegetables are going to be very rich in magnesium. So we lose magnesium through our sweat and urine primarily, and our kidney is going to regulate this loss of magnesium. Okay, let's talk about angiotensin 2. We've had some experience with this when we were talking about the endocrine system at the beginning of our course, and we also talked a little bit about it when we were doing the urinary system. But angiotensin 2 is a hormone that is going to be visited by two very important enzymes, not enzymes, but compounds here, renin and ACE. Right, but what we'll see is, all right, angiotensin 2 originally starts out in the liver, and it is an inactive hormone called angiotensinogen. The liver is constantly pumping this out, but it's inactive, so it doesn't really do anything. It's not until it encounters renin, and renin is released from the kidney, specifically from the juxtaglomerular apparatus there. And it's released because our blood pressure has decreased, or the sympathetic division of the autonomic nervous system has been stimulated. So renin will convert angiotensinogen into angiotensin 1. That angiotensin 1 will then travel throughout the circulation and eventually make its way to the lungs, where it will encounter our ACE enzyme. Right, that is our angiotensin converting enzyme, and that will convert angiotensin 1 into angiotensin 2, the active hormone. So what does angiotensin 2 do? Well, with the blood vessels, it causes vasoconstriction, and that will increase the peripheral resistance in our circulatory system. And if you increase the total peripheral resistance there in our circulatory system, you will increase blood pressure. And that's what I'm writing up here, a little formula for us. Blood pressure is equal to the heart rate times what we call TPR, which is total peripheral resistance. And so that's what we're doing. I know it's taken me a minute here to write this out, right? So TPR. So that's what we're doing. We're going to increase our total peripheral resistance, thereby increasing our blood pressure. Then the kidneys they'll start to decrease the urine output, thereby increasing or maintaining our blood volume. And so if you are maintaining or increasing the blood volume, you are going to increase the blood pressure. And so that is how angiotensin 2 is going to affect the kidneys. But we're not done with angiotensin 2. No, not at all. It's going to stimulate our thirst center there. So we're going to go into the hypothalamus, stimulate the thirst center. So that's going to encourage us to drink more fluids, hopefully water, maybe Gatorade, right? So we're going to drink some more fluids, and that too will increase our blood volume. And anytime we increase the blood volume, we of course increase our blood pressure. And angiotensin 2 is also going to stimulate, right, the hypothalamus to tell our posterior pituitary to release antidiuretic hormone, or ADH. And when we do that, all right, we are going to effectuate the movement of water through the use of aquaporins in our kidney there. And, all right, our angiotensin 2 will then stimulate the adrenal cortex to release aldosterone. And that too will help to offset that decrease in our blood pressure. So you can see here, all right, this picture should look familiar. We've seen it before, right, in the endocrine system. So here's our stimulus here. We're dealing with some low blood pressure going on, or the sympathetic division has been stimulated. And so that causes the release of renin, okay, from the kidney there. The juxtaglomerular apparatus is going to release renin into our circulation. So renin is going to meet up with the inactive form of angiotensinogen. It's going to convert it into angiotensin 1, which is still, right, inactive. And so this will find its way to the lungs. And then our ACE enzyme, angiotensin converting enzyme, is going to convert angiotensin 1 into angiotensin 2. Now we have an active hormone, and it's going to affect all of these different structures and tissues here. Like I said before, it's going to cause vasoconstriction, right? It is then also going to cause, right, a decrease in urine output, thereby increasing blood volume and blood pressure. As a result, we see a decrease in our glomerular filtration rate. We're going to stimulate the thirst center in the hypothalamus, so you'll drink more, increasing both blood volume and then thereby blood pressure. And then the hypothalamus is going to cause the posterior pituitary to release ADH, right, into circulation here, and that too is going to decrease, right, our urine output, maintaining blood volume. And then finally, aldosterone will do the same, all right, that will decrease our urine output and maintain blood volume. All right, I know this was a short video here, right, but I'm going to stop here, right, and my next video, I'll finish up talking about electrolyte and fluid balance. I hope you folks enjoyed this video as much as I enjoyed making it for you. Have a great day.